Okay, we're back. Math200, this is chapter 9. We're looking at 9.3. And what we're talking about here are exponential functions. So these are always true of every exponential function. They're one-to-one. So they pass, both the x's don't repeat and the y's don't repeat. The y-intercept will always be 0, 1. It's always going to go through y at 1, no matter what. If it's an exponential function, that happens. There is no x-intercept. It never crosses the x-axis. The domain is always all reals, negative infinity to infinity. And the range is always 0, not exactly 0. Well, 0 not inclusive to positive infinity, so greater than 0. All right? So those are always true of any exponential function. So this one happens to be, both of these happen to be exponential growth. If the base is a number bigger than 1, it's going to grow exponentially. If the base is a steeper number, it'll grow faster. You'll see it in the two graphs on the comparison here. So here, we'll do this one in red. So 0, 1, we knew that. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So that's going up pretty quick. And then negative 1, if I put in a negative 1, remember what that does. F of x equals 2 to the negative 1. Negative powers move it to the denominator. So that's 1/2. And then negative 2, it would move it down and square it. That would be 1/4. And so when we look at negative 1, it splits the difference between 0 and 1. That's 1/2. And then negative 2 gets it closer to 1/4. And so this is an asymptote, though. It'll never touch that. It'll get closer and closer to that, but never hit it or cross it. And this goes up, up, up really fast. Exponential growth. Things that grow exponentially grow quickly, all right? Let's look at that one. We have a negative 1. We pop in a negative 1. So that just moves the 4 down. That's 1/4. And then negative 2 is 1/16. So let's look at how these go. They have that common point, 0, 1. But then 1, it's already up to 4. 2, it's already off the chart. It's way up here. It's at like 16. And so 3 is way off the chart. It's at 64. 1, 2, and 2. 1, 2, 3. 1, 2. Wait, this one, 2. The red one, 1, 2, 3, 4. Had a 2 in there here. There's a 2. 1, 2, and 4. Sorry. So that one, I had to amend that. I went 1, 2, and then I went to 3, 8. So it's 2 right there. All right. So this one, it went 1, was 4. Oh, and then, yeah, 1, 4 was right. 1, 2. And then 2 was all the way up to 16. So that's off the charts. Let's do the little ones. It's 1/4 right away, and then 1/16. That's even closer. So this again is approaching the x-axis, but it'll never touch it. And it's going up steeper. So both of these are exponential growth. It's just with the base at 4 instead of 2, it's much steeper. All right. All right. In calculus, you'll look at curves and instantaneous rates of change at each different point on the curve. But this is algebra, so we're just comparing graphs. All right, again, the graphs are not going to be on the test, but they are going to be on the homework. So I want you to see a little exposure here. That's why we're doing these notes. What about number 2? It's, look at the base. It's 1/2 x and 1/4 to the x. These are also exponential functions, but these are exponential decay. These are decay functions. So look, they had, hey, put in 0, 1, 2, 3, negative 1, negative 2, and y So when I put in 0, anything to 0 power is 1. I put in 1, it's 1/2. I put in 2, it's 1/4. I put in 3, it's 1/8. Because think about it, that's 1/2 times 1/2 times 1/2. That's 1/4 times 1/2 is 1/8. -1 actually does the reciprocal, so that's 2. And -2 does the reciprocal and then squares it, so that's 4. All right, so let's take a look at that graph. And this is called exponential decay. So we've got 0, 1. 1 is 1/2. 2 is 1/4. 3 is 1/8. It's getting closer and closer to the x-axis. -1, it actually goes up 2. And -2, it goes up to 1, 2, 3, 4. The -2, a little too far over there. All right, so let's look. See, it's going down, 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 but it's getting closer to 0, but actually never hitting 0. So look, exponential decay, when it looks like this, it's half. So if I walk half the distance to the camera, and then I walk half the distance to what's left, and then I go half the distance of what's left, and then half the distance of what's left, half the distance of what's left, I'm going to get closer and closer, but I'm never going to actually hit the camera because each time I'm going half of what's left and half of what's left. And so the amount that I'm moving is approaching 0, but it won't ever actually be 0. It'll never actually hit the camera. All right. 1/4, it's really similar. It's 0, 1, 2, 3, -1, -2. So let's look at y. I put in 0, that's 1. So they have that 0, 1. Anytime it's an exponential function, it contains 0, 1. 1 is 1/4, 2 is 1/16, 3 is 1/64. -1 is just regular 4 because it does the reciprocal. And then -2 is 16. So in much the same way as the other one, 1/4, 1/16, 1/64. This is getting ever closer to 0 with not actually touching it. But then this way, it's up to 4 already, and the -2 is 16. It's way up high and going. So it's approaching 0 quicker. All right? So things that decay exponentially take a really long time to go away. So that's why they're always worried about plastic with the environment, because that takes a lot of plastics take a real long time to break down in like landfills and things. And so they have a really long half-life. It takes like a lot of years for half of it to go away. And then a lot more years for half of that, a lot more for half of that. All right, so here, let's look at page 9. They basically just want you to see the difference between exponential growth, exponential decay. So they said, look, if we have b to the x power, but the base is greater than 1, well, then what's going on? Well, that's going to be exponential growth. When the base is bigger than 1, you're growing exponentially. If you have b to the x, but b is between 0 and 1, meaning it's fractional, it's a fraction between 0 and 1, that's going to be exponential decay. It's going to approach 0, but never actually hit 0. And then it said, what happens if I do monkey around with the power? What if I take b to the x minus h when b is greater than 1? That didn't copy off. It should say greater than 1. All right. So if I play around with the exponent on this, what it actually does is it moves it to the right. The curve moves to the right 1 unit. Or like if it was 1, it would be 1 unit, or 2 units. It's going to move h units to the right. So here, let me show you what I mean. The normal exponential growth looks like this. But let's say h was equal to 1. a -1 would actually take it and move the whole curve 1 to the right. So it's not steeper, it's just it moved this point over and this point over and this point over and this point over. They're just all slid over 1 to the right. All right. And then it says on the next one, what happens if I go b to the x plus h when b is greater than 1? So that's exponential growth again, but it moves it to the left h units. The plus actually moves it to the left h units. And so if, again, we'll draw the original, the parent graph, if you will, exponential growth. Here we are at 0, 1. And then let's say h was +1. +1 would take that and move it there. And so the whole curve would move 1 over. And so it would be the same steepness, it's just slid over one unit. All right. And then they said, hey, let's play with that. That looks like fun. Let's give it a whirl. So they have us do a quick graph of f of x is equal to 2 to the x plus 2 power. And we got x and y, and we got 0, 1, 2, -1, -2, -3. So when I put in 0, I have 2 squared, which is 4. When I put in 1, I have 2 to the 3rd, which is 8. When I put in 2, I got 2 to the 4th, which is 16. I put in -1, that's 2 to the 1st. I put in -2, that's 2 to the 0. Anything to 0 power is 1. I put in -3, that's 2 to the -1, which moves it down to the bottom 1/2. All right. And so now if we look at that graph, we got, what do we have here? 0, 1, 2, 3, 4. That's right there. 1, 1, 2, 3, 4, 5, 6, 7, 8. That's right there. 2, 16 is off the charts. -1 is 2. -2 is 1. And -3 is 1/2. And so if we look at this curve, it's still exponential growth because the base is bigger than 1. So it's going to grow exponentially. But it's normally, this point is right here. The whole thing was switched and pushed over 2 to the left because of that +2. All right. Okay. Let's look at page 11 on our notes. That'll be fun with exponents, but now a little bit of algebra. Less graphing, more algebra. We like algebra. This is algebra class, right? So we like algebra. 6x is equal to 36. Find x. Well, look, this one's easy. If I go 6x and I go 6 squared is 36. Look, the only way that this could be true is if this power were the same as that power because they have the same bases. So basically, x is equal to 2. All right. Now here they're making it a little more challenging. So we got 9 to the 2x plus 1 power, and we got 9 squared. So again, when I have the bases are the same, the only way this could be true, equal, is if this exponent worked out to be equal to 2. So let's do that. 2x plus 1 is equal to 2, and then solve it. Back to week 1. Isolate the variable, move the 1 over to the other side, divide by 2, boom, 1/2. All right. Number 3 and 4, here, we can squeak 3 in yet. 1/27 is equal to 3 to the 2x. So this is 1 over 3 to the third power, right? 3 times 3 is 9 times 3 is 27. But I want it to be a 3. So look at what I'm going to do. I'm going to actually move that up and then make the power negative. Remember what negative power is? Move it down to the bottom and then you make it positive. Well, if I move it up, I have to make it negative. And now I have that base of 3. So we have 2x is equal to negative 3 and divide by 2. So x would have to be negative 3 halves, negative 1.5 to make this a true statement. If you throw in negative 1.5 right there and double it, that's negative 3. 3 to the negative 3 is 1/27. So that was a tricky one. Let's look at 4. It's also kind of tricky here. I'm going to put it blue. It's really hard to see anyway. All right. So let's look at 4 is 4 to the 3x minus 6 is equal to 32 to the 2x. Oh, geez. So this is really tough because now this, I can't make 4 into 32 with a power. I can make this 2 squared, though. X minus 6. And I can make this 2 to the 5th, 2x. And now remember what we do when we have a power raised to a power, we multiply. So look, I got 2 times quantity 3x minus 6, and I got 2 to the 5 times 2x. So distribute, I got 2 to the 6x minus 12 is equal to 2 to the 10x. And now because those are both base 2, I can just say, all right, the only way this is equal is if this exponent is equal to that exponent. And now back to your sweet solving skills. Isolate the variable, get all the x's on one side. Divide by the number in front of it. And x will equal negative 3. Whew, that was a tough one. All right, and then the last one here, application. You invested in a savings account, $5,000 at 6%, compounded monthly for 18 years. Find how much you have. Okay, so when you invest money, when you put your money in the bank and they pay you interest, that is exponential growth. It is that curve that goes up forever. It's just that when it goes up forever like that, you die there. And that's a lifetime. So before your money can really start launching, because that's just a little over 1, just a tiny little over 1. That's why in a lot of science fiction stuff, they have you put money in the bank and then you go in a time machine and then you come out and then you got all these millions of dollars and stuff. All right. Exponential growth. So here. This is just a plug and chug problem, and we'll have to use a calculator. All right, so the amount, let's see, we popped in $5,000, so that's P, that's the principal, the initial investment. 1 plus rate is 6%, but we gotta make it into a decimal. Remember, 6% as a decimal is 0.06. I always say to my students, you have to make it into a decimal so it can play with the real numbers. N is the number of times it's compounded in a year. So if it's compounded monthly, that would be 12 times in a year. So N is 12. And then we put it there also, 12. And then they want it away for 18 years. And let's see. Now remember, the 5,000 was yours to begin with, and 6% is amazing for a rate. That would be a heck of a rate of return. So here, 0.06 divided by 12, we'll figure that out. That's 0.005. So look at what we're doing. Order of operations again. We're doing parentheses. Within the parentheses, division before addition. We can do the 12 times 18. It's 216th power. So this is exponential growth, but look how this is just barely over 1. See how close it is to 1? It's just a little more than 1. So we can take that to the 216th power and see what that does to our money here. 5,000 times 1 point. Again, we do exponents before multiplying, so we're going to do the exponent to the 216th power. Almost 3 times your money. So I'm leaving that in my calculator and just hitting times 5,000. So you'll have $14,683.83 in 18 years. Your 5,000 became almost 15,000. All right. And that's it for 9.3. We'll see you on the next video, 9.4.